All right, so this practice question, like I said, comes from ACE Physics Syllabus Code 9702, paper 21 from October, November 2018. Question number 1 asks us to A, define displacement. Displacement is the net change in position. It is a vector quantity. It's measured in meters, but the definition of it is the net change in position, the total change in position. Because it is a vector, you could say something like it's the distance with the direction, right? Like distance is the scalar sort of corresponding scalar quantity. Acceleration is defined as the rate of change of velocity. The rate of change of velocity is acceleration. With an equation, you could say the change in velocity over the change in time. We should always kind of, state with a good sentence what the definition is. Don't just let your mathematical symbols stand as your definitions. If that helps you get to this, then good. All right, now it says B. A remote-controlled toy car moves up a ramp and travels across a gap to land on another ramp, as illustrated in figure 1.1. And you can see the figure there. The car leaves ramp P with a velocity of 5.5 meters per second at an angle theta to the horizontal. The horizontal component of the car's velocity as it leaves the ramp is 4.6 meters per second. The car lands at the top of ramp Q. The tops of both ramps are at the same height and are distance d apart. Air resistance is negligible. We want to first show that the car leaves ramp P with a vertical component of velocity of 3.0 meters per second. If we think about the information that's been given to us, we know the hypotenuse, the velocity vector, 5.5 meters per second. And we were conveniently given the horizontal component as 4.6 meters per second. And we were asked to show that this component, the vertical component, is 3. So you can think of maybe many paths to the solution there. I'm going to call the vertical component u sub y to be consistent with the symbols that we've been using previously in this course. And you could use Pythagoras' theorem to solve it, since we know the hypotenuse and one leg of a right triangle. We could also use this information and the cosine function to figure out what that angle is, right? So we know the hypotenuse and the side adjacent, so the cosine function, the inverse cosine of 4.6 over 5.5 would give us theta. And then by knowing the angle theta, we could use like the sine function or the tangent function to solve for u sub y. So those are the 2 ways that I could think of solving it. I'll give you a head start, so go for it. You kind of know the answer is 3. Right? You got to show that it's 3. That's all you Sometimes it's worse to be, told what the answer is, because then if you don't know how to do it, you're sort of forced to reconcile with your ignorance right then and there. But if you just solve something, okay, and you're like, hey, this might be it, right? You move on to the next one, and you won't know until it's graded. All right, so I'm going to use Pythagoras' theorem to solve this. 4.6 squared plus u sub y squared equals 5.5 squared, right? Keep track of the hypotenuse there, that's important. And in my calculator, I'm just going to solve it like this. 5.5 squared minus 4.6 squared equals something that I'm taking the square root of. 3.01 meters per second is indeed about 3. And so we've shown that it's that. To solve it the other way, we would say that theta is equal to the inverse cosine of 4.6 over 5.5. Right, because we know the side adjacent and the hypotenuse, the cosine function relates that ratio of sides. To solve for the angle, we use the inverse trig function. Right, so it's the cosine of the angle equals this ratio of sides, so the angle equals the inverse cosine of that ratio of sides. 4.6 over 5.5 is 0.836, and the inverse cosine of that allows us to deduce that the angle is 33.24 degrees. Knowing that, we could then verify this answer by saying, well, let me use my favorite, the tangent function. The tangent of this should be equal to this over that. So I'll just write that out so I don't make a careless error here in my working. The tangent of that angle equals the opposite over the adjacent. And that's in meters per second. So this will be in meters per second. And I've already got that angle in my calculator. Take the tangent of it, and then multiplying both sides of this by 4.6. I also get 3.01, which is also 3. So like, hey, that works too. Good. Moving right along here, it says, determine the time taken for the car to travel between the ramps. The time taken for the car to travel between the ramps. So here, I'm going to remember that at the top of the car's flight, right here, I could figure out the time to that point because I know the velocity in the y direction has reached a temporary speed of 0, right? So the same way that we have been solving these projectile motion problems, we apply the equations of motion, plugging in sort of what we know about it. If we can calculate the time here, we can double it to get the total time airborne. The equation that you're really using there is the definition of acceleration, right? So if acceleration is the change in velocity over the change in time, we could write that as v minus u over t if the initial velocity u is at time 0, right? And it's like t minus 0 is t. We rewrite this as v equals u plus at. That's the general form of the equation. Specific to this question, though, we could say that the velocity in the y direction equals the initial velocity in the y direction, and then the acceleration is that due to gravity. And I'm going to make it negative 9.81 times t, because the initial velocity y is positive 3. And gravity opposes it, so I need to make it negative relative to the initial velocity vector. It reaches a speed of 0 if it's moving 3 meters per second, then the term negative 9.81 t has to equal 3. And it's like 3 minus 3 equals 0, right? It's like that. We know kind of that's true, or we just think about it sort of with algebra. Don't get so caught up, though, in this calculation that once we solve for t, we report that value here. Remember, you should always reread the question that is asked of you. We're solving for the total time airborne, the time that it's going to take to traverse this gap. This equation here solves for the time to max height, where the velocity goes to 0. So you get out what you put in. Okay, we're putting in the velocity here, the initial velocity, so we're solving for the time to max height. And you might want to make like a note as you're sort of setting up the calculation to go, oh yeah, the final answer for time taken is going to be twice this. You know, that's my answer there. So negative 3 divided by negative 9.81 equals the time to max height, and then twice that would be our answer. Some students will just remember this algorithmically. They'll say, whatever the initial velocity in the y direction is divided by the acceleration due to gravity, that's the time to max height. The reason why that works is because of this equation of motion is valid, because gravity is a constant accelerator. Remember, these are the equations of constant acceleration. So 3 divided by 9.81 gives me this. And then if I double that, I get 0.61 seconds. It should be airborne for 0.61 seconds. The question goes on to say, calculate the horizontal distance d between the tops of the ramps. Horizontal distance d between the tops of the ramps. So the equation that you should sort of be mindful of here is the range equation. The horizontal distance is a range. Range equals vxt, where t is the total time sort of airborne. Okay? So they're calling the range D, the initial component and the constant component of horizontal velocity was actually given in the problem, 4.6 meters per second. All right, that's the constant horizontal component of velocity, and we've just calculated this to be 0.61 seconds. Some value meters per second times some value seconds. We can see what's going to happen with the units. The seconds will cancel. We're left with meters, which are indeed the units that we want to be in for range. So always kind of check the units. They should work out and help you find a mistake if you indeed made one. Multiply the time by the x component of velocity, 4.6, and we're solving this at 2.8 meters. Let's remember, 2.8 meters apart from each other. Part 4 asks, calculate the ratio of the kinetic energy of the car at its maximum height to the kinetic energy of the car as it leaves ramp P. If you are quick to write 0 down here for the ratio, because you say, well, wait a minute, it goes to a speed of 0 at maximum height, so it doesn't have any kinetic energy because velocity is 0. Then you should maybe catch your mistake by saying, well, it's a 3-mark question. Did they award me 3 marks just for that sort of conceptual understanding, or did I oversimplify this? So is the velocity 0 at maximum height? No. The y component is indeed 0. That's how we're able to solve it, because gravity only acts in that vertical direction. So we must apply this equation of accelerated motion only in the direction in which the constant accelerator gravity acts vertically. The reason why the car is still able to move and traverse the gap is because it has a constant x component of velocity. So you need to size up the question and say, hopefully I know the equation for kinetic energy, and then I can substitute in the correct velocity at maximum height. And it's not 0. Otherwise, the ratio would be 0 and we'd be done, and that probably wouldn't be worth 3 marks. The equation for kinetic energy, 1/2 mv squared, and we're comparing sort of 2 kinetic energies here. So if you initially sort of attack this question and go, oh, kinetic energy, I know that, it's 1/2 mv squared. And then you go back and you're trying to find the, oh, they must have told me the mass of the car then, right? If it's kinetic energy, and you read through all this information, you go, no, it's not there. They gave me an impossible question. Why would they do that? I thought they would always be able to solve it. Remember that it's a ratio, okay? And these factors, 1/2 m, are going to cancel. So the ratio of the kinetic energies is really a ratio of those velocities squared corresponding to those points. It's the same thing. So you can think about it as like a ratio of kinetic energy measured in joules, and the joules will cancel, or a ratio of velocity squared, and the units meters squared per second squared will cancel. It's just a ratio, so the units are going to cancel however you sort of think about it. But we don't need to know the mass if it's a ratio, because the mass will cancel. What is the velocity of the car at maximum height? In the y direction, it's 0, but remember, at maximum height, that's where we can figure out the time, because gravity slowed it down to a stop in the y direction, but it still has this constant x component that it started out with, right? So the 4.6 meters per second here, here, and here, right? It maintains that x component of velocity. It's constant. So it's 4.6 meters per second. Again, the units don't matter so much for this ratio. And then the velocity as it leaves the ramp, what's that? 5.5. Like, it really is going that fast. And like mathematically, we could describe it as, oh, 3 meters per second up, 4.6 meters per second over. So Pythagoras' theorem, relates those. That's how we add them up. But that's its actual velocity, right? It's moving at that speed, 5.5. That's why it takes sort of this path in. So the ratio is just 4.6 squared to 5.5 squared. .7. Let's take a moment to really consider this now. The ratio of the energy, the kinetic energy it has at maximum height, is 70% of what it had when it left the ramp. So like it has a certain amount of kinetic energy here, and here it still has 70% of it, right? The ratio of the kinetic energy at the top of its flight to the kinetic energy it possessed as it left the ramp is 0.7 or 70%. Where did the other energy go? Does anybody know? Where's the other 30%? You could say it's like we wouldn't want to say it's destroyed, right? Because we kind of know better, like energy is never created nor destroyed, but you can't say like gained and lost. That's better language. So say, okay, it's lost to what, right? It's converted into something else. Those are both good ways to sort of think about it. So I would sort of ask a follow-up question. It's lost to what? It's converted into what? Potential energy due to gravity, right? It's going higher up in Earth's gravity field. And so it's spending some of that kinetic energy being converted into potential energy. When it lands, it's converted it all back again, right? So it lands with the same amount of kinetic energy that it left with, provided these assumptions are, hold, like there's no air resistance, there's no energy losses, it doesn't make a sound as it, travels and so on. I'm gonna show you a video today that sort of previews next week's study of momentum, where we like to sort of idealize motion in physics sometimes, even though in reality, like, yeah, there's energy, there's heat losses, there's friction, there's, other things going on. All right, so that's point 7. The final part of this paper says ramp Q is removed. The car again leaves ramp P as in B and now lands directly on the ground. The car leaves ramp P at a time t equals 0, lands on the ground at time t equals capital T, which is the end of our plot. And it says on this figure 1.2, sketch the variation with time t of the vertical component, v sub y, of the car's velocity from time t equals 0 to time t equals capital T. Numerical values are not required. So here we just got to kind of think about, it leaves the ramp with a non-zero velocity, +3, right? And I want to call +3 like maybe this point right here. The reason why I'm not going to make it the very top is because if I remove the ramp Q, this thing is launched at a speed of 3 and it's going to decrease, right? Gravity is accelerating. So it's a constant sort of slope like this. Eventually it reaches a speed of 0. That's at this point, right? It goes until it's at a speed of 0. So sometime after it's launched, it's going to be at that speed. In fact, it's the same time, 0.3 seconds, the half of this time here. So after 0.3 seconds, it's still at the top of its flight, but now instead of having this ramp here, instead of reaching sort of a symmetric -3 meter per second landing speed in the y direction, it's going to go faster than that, right? Gravity's going to keep accelerating all the way down. So symmetry of motion would look like kind of like this, okay? Where this would be like what the motion is already, okay? In other words, this is the motion when it does land on the ramp because it lands, so if this is +3 up here, this is -3 down here, it lands with the same speed, but just in the opposite direction. And these sort of, the areas here and here are equal, right? Because it falls the same height that it went up. But because we've removed the ramp here, how is this plot going to change? Well, we just need to extend this until it reaches time t when it hits the ground. And so no longer do we have that symmetrical sort of, oh, it falls down as much as it went up, but rather it's going to continue to fall. And I should have maybe scaled it slightly differently so I could actually get my, but at time t, it's there, okay? So some line like this, you couldn't start at the top and then just go down to here because then you still have that symmetry. You need to show that, oh, it's falling further, it's getting a faster negative speed than it started out, right? So you need to extend that beyond, right? And then this would be sort of what a plot would look like.